Welcome to this video. My name is Phil and I am a senior lecturer in astrophysics at the University of Lincoln, and in this video I wanted to go over the transit method again. This is a method for detecting exoplanets around stars. So exoplanets are planets orbiting stars that are not our sun basically, so these are not in our solar system. Now when we detect those, they actually pass in front of the star, so basically line of sight between Earth and the star. They will block out some of the light from the star. We get a dip in the brightness, and that's how we basically detect them. Now, if it was a single planet orbiting one star, we would expect the timing between each transit to be fairly constant. We wouldn't expect it to change. However, there are a few different reasons as to why the timing between transits can actually change. Some of those are actual physical changes in the timing, so something's actually changing the reason as to why it's lengthening or increasing, decreasing, or there are other reasons why it can be apparent. So it might appear to be shorter or longer than it should be. And this one is going to look at the parallax, and that will alter apparently the timing between the actual transits itself. So the transit method, just a quick recap really. If a planet passes in front of the star as we look at it, it should block out some of that light. We then get a dimmer star. And as that planet passes in front, we get a fairly characteristic U-shaped dip like that there. Now, if we were to measure one transit, we waited and then we got the next transit, so as it orbits around, it will come and transit a second time. We would expect the time between that to be fairly constant, so then the third transit should be about the same length of time that it was between the first and the second. So that's typically what we would expect. However, as I mentioned, the time between each one can actually change. And this is an example of one here where you can see each transit actually is slightly different. So if they have the same time between each one, you then put the next one below it and then below it, you can see that actually it's either early or later. And again, there's a variety of different reasons as to why that can actually occur. This one's going to be parallax. So what is parallax? Well, it's the observed displacement of an object, in this case a star really, with respect to its background stars from our point of view. What does that actually mean? Well, example here, parallax is from our movement around the sun. So as the Earth goes around the sun, we basically are moving in one direction, but we're looking at a star, and that creates an angle basically. So we're looking at it from an angle. So from one side of Earth's orbit to the next, there'll be some angle which is the parallax angle. That changes depending on how far away it is. Stars that are closer will have a larger parallax angle than ones that are further away. So actually, it's worth noting that this particular effect for changing the timing on a transit is going to be more relevant for stars that are quite close to us. As you get further away, then it becomes less significant. So close stars, you're going to get this more. But if we look at a star, what we would actually find is that the background stars would kind of appear to be in different locations. So we focus on that star, and as we go around our orbit, then the background stars will appear to shift, and that's basically parallax. And because of that, and there's a geometric change, or the configuration of that is changed, it means that the timing of the transit will also slightly change. So every 6 months, we're going to be at the extremes of Earth's orbit, basically. So example here, we would expect the biggest parallax from one point of the year, then go to 6 months, basically, and we'd get that would be our maximum parallax effect, essentially. So because of that, we do get a change in the viewing geometry. So if we imagine when the planet starts to begin its transit, the first one on the left-hand side there, if we then go around 6 months, when we start to see that transit occur, it's going to be at a slightly different time. Why is that? Well, to get into the same sort of configuration, the planet either has to go around slightly further or slightly less on its orbit around its star. And because of that, it changes the time between each transit, because each transit relates to its orbital period. But we're changing how far around it's actually going. Again, this is an apparent change, not a real change. So actually, if you had something like the tidal decay of a planet, where it was actually spiraling inwards due to tides, then you would expect it to get shorter, basically. But that would be its actual orbital period changing. The orbital period in the parallax here is not changing. It's just how we're actually viewing it. So if you want to calculate the change in the transit time, so the difference between each successive transit, we can use this equation here. and it relates to the mean orbital radius of Earth, which is going to be 1 AU. That's the distance between the Earth and the Sun, averaged out over 1 year. You've then got the orbital period of the actual exoplanet itself, and then the distance to the star. So you should be able to see here, really, that as you get further and further away, then your transit or your change in transit time is actually going to get less. So it's only really going to be relevant for exoplanets and stars that are going to be quite close to us. As you get further and further away, that change in transit time is going to get smaller and smaller to the point where it will be almost negligible. So, yeah, just to mention, it will decrease with decreasing orbital period. So for hot Jupiters, it's going to be negligible as well because they have really short orbital periods. And then as you decrease the distance, it will increase the actual change in transit time, actually. So an example then. Let's finish with an actual example to give you an idea of how much the time difference is actually going to be due to parallax. So we've got an exoplanet that has an orbital period of 400 days, so a little bit longer than Earth. It's going to be at a distance of about 10 parsecs, which actually is relatively close, relatively nearby. That's going to give you a change in the timing of the transit by about 5 seconds. So actually, it's not a huge amount, but it is also measurable. So we do need to take this into account. But again, worth noting, it's probably for your really nearby stars. If they're like 100 parsecs more, this effect's going to be reduced down to be almost negligible. So thank you for watching, and if you enjoy, then do check out some of the other videos.